Okay, so last time we were going through the classification of surfaces now that we proved all the main theorems. So we were in the Kodaira dimension 1 case. And we had showed that if X is a minimal model with Kodaira dimension 1, then the anti-canonical linear series, or some large multiple, is an elliptic vibration. And so to classify such X, we wanted to classify elliptic vibrations. And so we did this in 2 steps. Step 1 was classify the fibers. And then step 2, which is the last thing we were talking about, was the canonical bundle formula. Which essentially lets us classify the base as well as the variation of the family. So let me recall the actual formula. So more generally, let alpha from X to C be a relatively minimal meaning no -1 curves in the fibers, elliptic vibration. And suppose that there are multiple fibers M1, F1 through Mn, Fn. So these multiple fibers were fibers of the form take some IN fiber. Let me use a different letter. ID fiber, which is some loop of P1s, or maybe an I0 or an I1, which is a single nodal elliptic curve or a smooth elliptic curve, and then multiply them by some numbers. So take a multiple. So these fibers are non-reduced fibers where everything is an integer multiple of a fiber that looks like a loop of P1s or a nodal cubic or just a non-singular elliptic curve. And M is this multiplicity. Okay, so look at all these multiple fibers. So there are other types of singular fibers, but in the canonical bundle formula, it's the multiple fibers that make a contribution. Then the canonical bundle of X is the pullback of the canonical bundle on C, tensor this line bundle R1 alpha lower star OX dual tensor OX twisted by a contribution for these singular fibers, for these multiple fibers, which is the sum of mi minus 1 fi over multiple fibers. Okay, so that's an equality of line bundles, but we can turn it into an equality of Q divisors. So we can write it as the canonical bundle of X is the pullback, or the canonical divisor is the pullback of the canonical divisor on C plus some line bundle L where this line bundle is O of L, or this divisor is O of L, plus some contribution B from these multiple fibers, where B is sum mi minus 1 over mi times the point pi, where the multiple fiber mi fi is the preimage of this point pi. So here basically you just said to make everything pulled back, well, mi minus 1 times fi isn't pulled back from the curve, only mi times fi is. But if I divide everything by mi and think of it as a Q divisor, then we do get a pullback like this. And here, maybe to be more precise, I should write equivalent as Q divisors. And then the other important piece of information in this formula is that the degree of this line bundle R1 alpha lower star OX dual is the Euler characteristic of OX. Okay, and then I made some remarks about this formula. Any questions about the statement? Okay, so let's sketch a proof of this. Okay, so the main point is a lemma that follows from the classification of all the possible singular fibers plus some extra work. Two parts. One, if we have a multiple fiber, so let's say this is one of our multiple fibers, then the canonical divisor, or the canonical sheaf of F is trivial. And the line bundle OF twisted by F, so this is roughly the normal bundle of this reduced fiber F, is a torsion line bundle of order M. So, of course, if we look at OF twisted by F to the M, we get OF of MF, which is the same as the pullback from the curve restricted to F, which is trivial because F is inside of a fiber, and so we're pulling back. So the content here is that it's exactly order M, that any lower power of this line bundle is not trivial. Okay, and so that first part, I won't go through the details, but essentially follows from the classification, because you can just check in all these cases that the canonical bundle really is trivial in these loops of P1s and in this nodal cubic, and then in the smooth elliptic curve case. And then you have to do a little more work to check that the order is exactly M, but I'll leave it at that. And then the second point, when really the first point was really to prove the second point, which is that the cohomology of the structure sheaf is constant. So if you look at global sections of a fiber, or if we look at H1 of a fiber, these are both 1 for all P. Okay, and this is obvious for smooth fibers, because smooth fibers are elliptic curves, so they have H0 is always 1, and then H1 is 1 because of the genus. If we look at integral fibers, the reduced and irreducible ones, then the same kind of argument works. The difficulty here is checking it for these multiple fibers, which follows from 1, and for non-reduced fibers that aren't multiple fibers. so fibers that have some reduced components and some non-reduced components, and there you have to kind of induct on the components and use the fact that there are no -1 curves, that there are these special configurations of just -2 curves to get this. But this is the most important part, really. So what does this buy us? So if we look now at H0 for any fiber, if we look at H0F, with coefficients in the canonical restricted to that fiber, well, by Serre duality, this is, well, first by junction, I guess, this is H0 of F, comma, the canonical of the fiber. And then by Serre duality, this is H1 F OF. So here, okay, this is a junction. And here you have to believe that Serre duality works for singular curves, but with singularities that aren't so bad. Here they're all Gorenstein curves. They all live on a smooth surface. Okay, and then by our lemma, this is 1. But this is true by our lemma for any fiber. So now we can invoke Grouart's theorem, which is maybe a special case of general cohomology and base change results, which essentially says anytime you have a line bundle so that the global sections on every fiber have the same dimension, then when you push forward that line bundle, you actually get a vector bundle whose rank is equal to this dimension. So Grouart's theorem tells us that alpha lower star of omega x, or of OX twisted by KX, same thing, is a line bundle. And its fibers are exactly these global sections of OX, KX restricted to F. They're all one-dimensional, so it's a line bundle. And here we're using that our base scheme C is a reduced curve, or just a reduced scheme in general. Okay, so now we have this line bundle. But now by adjunction, if we pull back, sorry, a different type of adjunction than the adjunction up here, just by an adjunction of functors, we have a map like this. Just the universal, the co-unit of adjunction for pullback and push forward. So we're going to use this to compute this formula. So essentially, what's going to happen is that this term having to do with the multiple fibers measures exactly how far from being an isomorphism this co-unit of adjunction is. And then this other term comes from computing alpha upper star, alpha lower star of OX of KX. Okay, any questions up to there? Okay, so first observation. Let's call this map lambda. Lambda is an isomorphism on the generic fiber. And to see this, we write down, so on the generic fiber, we have just a smooth curve. And more generally, if we restrict to the smooth locus, so let's say U in X is the locus where alpha is smooth, which contains this generic fiber. Then on this locus, well, we always have this formula in terms of relative canonicals, that the canonical of X is the pullback of the canonical on C tensor with the relative canonical, essentially the definition of the relative canonical. But now if we restrict this to our smooth locus, this is alpha upper star omega of whatever the smooth locus on the base is, tensor. Well, now we're on this locus where the fibers are smooth, so this relative canonical is really just the relative differentials. And now if we restrict this further, then we get, which is contained in this U, then we just get omega x eta is equal to something pulled back from the base, but now we're on a fiber, so that's just trivial. So this term becomes trivial. And then this term, because it's on the smooth locus, so it's actually relative differentials, just becomes like I don't know, maybe this is a stupid way to write it, but it's trivial because it's an elliptic curve. Because x eta is genus 1, so it's the kind of fiberwise differentials are trivial. Okay, so maybe that was a little stupid way to explain it. I could have explained it simpler, but that's the point. So it's this lambda has to be an isomorphism on this generic point. And so whatever the difference between these two bundles is, it has to be contained inside of fibers. So let me write it as OX of KX has to be of the form alpha upper star, alpha lower star, OX of KX, tensor, some OX of D, where D is effective and contained in fibers. So you should think in general, like what's going to happen in higher genus is that this won't be true anymore, because now this omega x eta will have some components as well in higher genus. And so instead you'll get something contained in fibers that measures singularities of the fibers, as well as some horizontal stuff coming from the genus. So this is what's special about genus 0 here, that we only have stuff contained in the fibers as our correction coming from this junction map lambda. Okay, so then we can compute. So we know kx squared is 0. And then according to our formula, the canonical divisor then is something pulled back from the base, just whatever the divisor corresponding to the line bundle alpha lower star O of kx is, plus this d, whatever this d is. But now this alpha upper star b is pulled back from the base, so its self-intersection 0. D is contained in fibers, so its intersection is 0 with this b, and so this is just d squared. So whatever d squared is, it has to be 0. But then we have the Hodge index theorem, which says that if we have some divisor contained in fibers whose square is 0, then it has to actually be a multiple of fibers. So it has to be some uniform multiple of some complete fiber. Or maybe I'll write it as Ni times alpha inverse Pi. Okay, and now we compute with the junction again. So yeah, let me stick to calling this Fi actually. Okay, so a junction tells us this, but now we look at our contribution of the canonical to this fiber Fi, and it's exactly this D, because the rest of the canonical is pulled back from the base, so it'll intersect Fi trivially. So the only thing we'll get here is that this is the same as OX of Ni Fi plus Fi restricted to Fi, because the other piece of the canonical is pulled back, and the other components of D are disjoint to F. So kind of D is some sum. I really should put sum here. Is some sum of multiples of fibers. And now this is OF Ni plus 1 Fi. But on the other hand, by our lemma, this is trivial. And so now the other part of our lemma tells us that Ni plus 1 has to be the multiplicity. Okay, so there's one thing maybe I skipped here, which is that whatever these Ni are, well, they're greater than 0, because if there's 0, then there's no contribution from D. So we're only looking at the ones where there is a contribution. But they actually have to be smaller than the multiplicity. So that's maybe, we'll leave this as an exercise. Okay, so then that implies that Ni plus 1 is Mi, or that the multiplicity is exactly Mi minus 1 for these multiple fibers. And so that's exactly what contributes to D. Okay, so that gives us this term underlined in red, and that's our D. And now we need to compute the other term. So the other term is exactly this alpha lower star OX of KX. So next we need to know what this is. But this is the same by the usual formula for the relative canonical. This is the same as alpha lower star alpha upper star omega C tensor relative. And then by projection formula, this is omega C tensor push forward of relative. And then we have relative Serre duality, or maybe relative growth inequality. Which tells us that the push forward of omega x over c is the dual of the first cohomology, because we have a relative dimension 1 map. Okay, and then this is literally just if alpha was the map to a point, this would just be regular Serre duality that says H0 of the canonical is the dual to H1 of O. And this is the relative version. Okay, so that gives us our formula. And then the last thing is to compute the degree of this, and that is, well, basically use Riemann-Roch to compute chi of OX, and then with the caveat that you also want to use the Leray spectral sequence. So chi of OX will be written down in terms of some cohomology groups of O, and then we can use the Leray spectral sequence plus some Serre duality to manipulate it to get that chi of OX is minus the degree of this R1 alpha lower star OX. Whew, okay, so that's a sketch of the canonical bundle formula. Are there any questions? Okay, so then that finishes the classification for Kodaira dimension 1. Well, kind of. This gives us the tools to then try to classify elliptic vibrations, which will classify Kodaira dimension 1 surfaces. So now we're left to understanding the structure of Kodaira dimension 2 surfaces, or minimal models. So let's say X is a minimal model of general type. Then, by abundance, we know that we have a base point free linear series that maps X onto some Z, where now the dimension of Z is 2. And in fact, we know more because we actually know that the Z has to be proj of the canonical ring of Kx, of the ring of sections of Kx. Okay, so now we want to analyze the geometry of this Z. So let's suppose we have some exceptional E. So we have some exceptional curve. Well, we know that E squared is less than 0 by Hodge index theorem. And then we also know that Kx dot E is exactly 0 because it's the fiber of this base point free linear series that's a multiple of Kx. So if we compute the canonical of E, well, the first term gives us 0, the second term gives us something negative, so the canonical of E is strictly negative. So if E is irreducible, that means it has to be P1. Which then means that E squared is minus 2. So this E has to be a minus 2 curve. And so this phi has to, like the fibers of this phi, the exceptional loci of this phi have to be unions of minus 2 curves. But they have to be genus 0 unions, because if we ever get some kind of loop in there that's genus 1, then we'll get 0 for this intersection when we take E to be that loop. And that's impossible by the Hodge index theorem. So again, so kind of any collection of curves in the fibers of phi have to have negative definite self-intersection. So when E is just a single curve, we get that it's a minus 2 curve, but that also tells us that E squared has to be strictly less than 0 for any collection, for any like sum, non-negative sum of these curves. So that tells us that the exceptional locus of phi is some union of trees, so disjoint union of trees of minus 2 curves with negative definite intersection matrix. And now you can just classify all the possible configurations, and these are again classified by Dynkin diagrams. And so we saw these in the classification of fibers, but these are not the extended ones. These are just the regular Dynkin diagrams. And so what is this map doing? It's contracting curves with these ADE configurations, and then there's some more classical surface theory tells you that Z has what are called ADE singularities. At points where some -2 curves are contracted. So this is the first place for surfaces that we see singularities, and we see them precisely because we're now contracting -2 curves instead of just -1 curves. Okay, but they're all completely classified. So the first thing we know about Z is that it's birational to X and it has singularities, but they're just AD singularities. Another name for these that generalizes to higher dimensions is canonical singularities. And the reason they're called that is because we saw the Z is proj of this canonical ring. So these canonical singularities are equivalently the singularities you get when you take proj of a canonical ring in the case of Kodaira dimension 2. So in the general type case where the proj is the right dimension. And now we also know a bit more. So anytime you have this type of contraction where the fibers are connected and your target variety is normal, if you look at Picard, you actually have that the pullback map is injective. And then you can describe the co-kernel here. It's essentially this co-kernel is determined by just restriction to the exceptionals. So this maybe the best way to write it is it's the direct sum of copies of Z over E exceptional curves. So you always have this type of exact sequence whenever, let's say, phi has connected fibers and everything's normal, and phi is birational. So phi is birational with connected fibers to something normal. Maybe you can compute this. Using that Picard is H1 X OX star, and that F lower star, alpha lower, I don't know what I called it, phi lower star, and that phi lower star of OX is OZ. And so this is a piece of the exact sequence. This is like the low degree exact sequence of the Leray spectral sequence. So that's how you get this sequence. But what this tells us is that if we have some line bundle on X that's intersecting 0 with every exceptional curve, then it's actually pulled back from a line bundle on Z. That's the upshot of this exact sequence, and vice versa. If we have a line bundle on Z and we know it's pulled back to X, then we know the line bundle on Z. So the upshot of all of this is that Kx then has to be the pullback of something on Z. But on the other hand, Z has these finite singular points, this discrete set of singular points, and away from those singular points, Z and X are isomorphic. So whatever this line bundle is, it has to be the canonical bundle on the smooth locus, because on the smooth locus everything agrees with X. But Z is normal. So if we have a line bundle and we know what it is away from codimension 2, then we know what it is on all of Z. So actually, this implies that L is just the canonical bundle of Z, which is really a Cartier divisor for these AD singularities. So we'll talk a little more about working with the canonical divisor when you have singularities, but in this case, these AD singularities are Gorenstein, so we have an actual canonical line bundle. Okay, so this tells us that Kx is the pullback of KZ. And so KZ is ample. So that's the most important point. So any curve, if we have any curve through Z, we can take its pre-image in X, and this will be some curve that's not exceptional plus some exceptionals. So then if we intersect KZ with any curve, this is the same as intersecting KX with a curve plus some exceptionals, which is strictly positive because this curve isn't contained in the exceptional locus, so it has to be KX positive. So maybe the better way to say it is that if C is not exceptional on X, then KX.C is strictly positive because this phi is exactly contracting the zero curves. So that implies that KZ.C prime is strictly positive for any C prime in Z. So that's how we get this. Okay, so our upshot then is that the outcome of the minimal model program in this classification in the general type case is that we have a minimal X and then a contraction onto this Z, which we'll call the canonical model, which on the one hand is proj of the canonical ring of X, but on the other hand is uniquely characterized by the two conditions that I wrote above. One, having canonical singularities, or these ADE singularities. And two, having the property that KZ is ample. So that you can make that into a definition that a canonical model is either proj of a canonical ring, if it makes sense, or it's a variety with canonical singularities on which the canonical bundle is ample. And then from here, you can use this to classify these possible Z's by using the canonical to embed into projective space. And then, so you have to do some more work to understand the canonical linear series when it's ample, when the canonical is actually ample, and that gives you embeddings into projective space. And then you can, for any fixed class of Z, you can try to understand its canonical embedding, and then use that to understand the Z's. Okay, so that finishes classification of surfaces. Are there any questions about basically anything we've done so far? Okay, so that finishes surfaces. Okay, so now for the rest of the class, we're gonna work in higher dimensions. So maybe I'll just write down our goals for the next bit of the class. We have to prove the cone and contraction theorems. For the cone theorem, we're going to give two different proofs. One of them works only in the smooth case, but soon as we try to actually run the minimal model program in higher dimensions, we're going to get singularities. So then we need to actually prove it in the singular case as well. And so that'll necessitate proving the base point free theorem. And the rationality theorem. So we'll review all of this, but I just wanted to give some kind of heads up. And to prove these theorems, we'll need some vanishing theorems. So we'll spend some time proving vanishing theorems, both in the smooth and the singular case, the Kodaira vanishing theorem and Kawamata-Vivek theorems, and also a non-vanishing theorem, which was an analog of our non-vanishing theorem for surfaces that minimal models had pluricanonical sections. It's unfortunately not that strong in higher dimensions. I mean, strong enough to prove all of these things, but it's not. We don't know the full theorem that if you have a minimal model in higher dimensions, there are pluricanonical sections. So it's a slightly different flavor, but the same type of theorem. Okay, so that's where we're going, at least for the next maybe month and a half. Yeah, and then we'll see the last few weeks what's going to happen. Okay, so let's just jump to the cone of curves in higher dimensions. Okay, so before I only defined intersection products and numerical equivalences for surfaces. So let's just set up notation and define everything in general. So let's say X is projective. Then we can still define for D a Cartier divisor and C a curve. We can define this intersection product just like we did before, where we look at this embedding and we take the pullback of the line bundle OX of D under this embedding and take its degree. So that gives us the intersection product between divisors and curves in general. So then if we have some integral, sorry, not integral, if we just have some formal combination of these curves, i.e. a one cycle, then we can define, we can extend this intersection by linearity. And we can define numerical equivalence of curves now. So C is numerically equivalent to C prime, where C and C prime are some one cycles, some formal combinations of curves, if and only if D dot C equals D dot C prime for all Cartier divisors D. Okay, and then we have N lower one. And whenever there's no subscript, that'll mean that these coefficients are real. But we'll also need rational and integral sitting inside of it as numerical equivalence classes of one cycles with real coefficients. On the other hand, now we also have a different vector space, N upper one, for divisors, which is the Néron-Severi tensor R, where this Néron-Severi group is divisors up to algebraic equivalence. So we can write it as pic x mod pic 0 of x algebraic equivalence is exactly the equivalence of modding out by the connected component of the identity of the Picard. So that's what this pic 0 is. And in general, we actually know, so we have a pairing like this given by intersection. So the pairing, the intersection product extends by linearity. And we actually know in general that the dimension, so this is a perfect pairing. And we know in general that the dimension of this N1 is finite. So we already saw this in the smooth case using some topology. So in the smooth case, you do this by embedding N1 into H2 real, where you look at the fundamental class of some curve. But in fact, so in the smooth case, this is less than or equal to the second Betti number, which is finite. But in fact, it's true more generally. Okay, and maybe the philosophy in higher dimensions, or an important point, is that so on surfaces we had both curves and divisors, and they were the same thing. So every time we were working with the curve, it maybe wasn't so clear whether the important thing was that it was a curve or the important thing was that it was a divisor. And the philosophy that was first introduced by Mori is that in higher dimensions, we should be studying birational transformations from the point of view of curves rather than divisors. So like we use divisors to build birational maps via linear series, but to actually understand the geometry of these linear series, we should be looking at what's going on in curves. So kind of the focal point should be n lower 1 of x. Okay, so let's define then our cone of curves, just like before. So the rational cone of curves, NEQX. I think NE stands for numerically effective, because we're looking at numerical equivalence classes and we're looking at effective curves. So this will be the sum. So all formal linear combination sum AI CI, where this means the numerical class where AI is rational and non-negative. And then we have the real counterpart, which we'll just call NE of X with no subscript. Same thing, but where AI is real and non-negative. And this all sits inside of its closure inside of the vector space n lower 1. Okay, so this is the the kind of important object that determines the birational geometry of X, at least up to a certain point. Okay, and let's just set some notation. So if D is a Cartier divisor, or even Q Cartier or R Cartier, which just means an element inside of one of these larger spaces where you tensor up to R or to Q, then we can define D greater than or equal to 0 as just the numerical classes whose intersection with D is greater than or equal to 0, and then similar definitions with greater than, less than or equal to, and less than. That's just some useful notation. And then given our closed locus any bar of X, the subscript D greater than or equal to 0 will denote the intersection of these two regions. And similarly with greater than, less than or equal to, less than. Okay, and now we can restate Kleinman's criterion in this notation and in general. And next week we'll say a few more words about generalizing this even further and some sketch of a proof. But in this notation, then Kleinman's criterion says if X is projective, and D is Cartier, then D is ample if and only if the locus D strictly greater than 0 contains the full cone of curves minus 0. So that's a restatement of Kleinman's criterion in this notation. So let's draw a picture and then write down a corollary from this picture. So we have our cone of curves, which we saw a bunch of examples earlier. It could be quite complicated, but it's some kind of cone like this. There's the origin here, and then given our ample divisor h, if we look at the hyperplane where h is 0, that's going to pass through 0, but Kleinman's criterion tells us that this whole cone is contained in the half space h strictly greater than 0. And then from this picture, we immediately get some corollaries. So 1, any bar of x doesn't contain a line. So a priori, it could be that both C and minus C are equivalent to effective classes. And on a non-projective variety, there's no reason this can't happen. I don't have an example off the top of my head, but this is saying on a projective variety, when you have an ample, this can't happen because everything has to be on one side, contained inside of a half space on one side of an ample, and a half space can't contain any lines. So 2, if we take instead of h equals 0, maybe we shift things a bit and we take h less than or equal to some constant c. So look at the locus where h intersects curves less than or equal to some constant c. Maybe that'll slice something like that. And then if we look at the region here with any bar, from this picture, we get that whatever the intersection is has to be compact. So that's 2. So the set of classes such that h dot z is less than or equal to c for any constant fixed constant c is compact. And then corollary 3, which follows from 2, is that the set of integral classes now, meaning with integer coefficients, that are effective or pseudo-effective, with h dot z less than or equal to c is actually finite. Because these integral ones are lattice points inside of this cone, and we have some compact set, and so the lattice points inside of this compact set have to be finite. Okay, so those are some nice, pleasant consequences about the cone of curves from Kleinman's criterion. Okay, so now we're ready to state the cone theorem in almost full generality, but at least to state it more precisely than we did for surfaces. I'll give myself some room. And we'll call this cone theorem 1, which is the first version of the cone theorem that was proved by Mori. But we'll prove a much more general one later. So let X be smooth projective. Then there exist countably many curves and not just any curves, but rational curves. So kind of the two important points are that there are countably many and that all these curves are rational. Let's index them ci over the integers, such that 1, the cone of curves is of the form stuff that intersects the canonical non-negatively, which we can't say anything about. And in fact, we saw some examples where we can't say anything about this, like in the abelian variety case, where there was some round cone and that's it. Plus some sum of these countably many rational curves where the intersection of the canonical with these rational curves is negative, I guess, which is implicit in this decomposition, but we actually know more. We know how negative it can be. So where 0 is less than or equal to minus kx dot ci is less than or equal to, I guess here it's really strictly less than. 0 is strictly less than minus kx ci is strictly less than the dimension of x plus 1. Okay, so this is saying there are these countably many rational curves that have this bounded negative intersection with the canonical, and that they span the negative side, the canonical negative side of the cone of curves as a cone. And then 2, oftentimes you'd like for there to only be finitely many curves you have to work with. And 2 says that you can guarantee finiteness as soon as you perturb the canonical by any ample divisor. So for any ample h and any epsilon greater than 0, if we write down the same decomposition where we replace kx with kx plus an epsilon multiple of our ample, then we actually only need finitely many of these curves. Okay, and I'll draw a picture in a second, but I want to kind of rest on the statement and wait for questions. Okay, so let me draw a picture then. So we have our cone of curves. Here's the hyperplane kx equals 0. And here we have the half space kx is strictly less than 0. So we have this region over here where we just can't say anything about. It can be arbitrarily complicated, and this is any bar x kx greater than or equal to 0. And that's just whatever it is. But then on the negative side, we have these countably many rays, which are spanned by rational curves. And so they're rational polyhedral because they're spanned by actual curves, not just real curve classes. So they have rational slope, and there's countably many of them. So we get something that's like at least locally polyhedral. But a priori, there could be accumulation points because we just know countable. And 2 tells us the only accumulation points for these rays are on the boundary kx equals 0. So 2 says that if we take some ample, so we start with some ample, which lives over here. So here's h equals 0, because the full cone of curves is contained in h greater than 0. If we look at some really small multiple of this h plus the canonical, it's going to slice it something like this, maybe. Then on the negative side of that hyperplane, then we actually just have finally many curves. So whatever accumulation points we have can only be in this kind of small gap between kx plus epsilon h equals 0 and kx equals 0. So there really could be countably many, but they're all accumulated along that hyperplane. Anytime we're in this region away from that hyperplane, we actually just get countably many. I mean, we actually just get finally many, so we actually get something that's really polyhedral. And then the last thing is that part of the way we're going to prove this, which is something that we already briefly talked about before, is we're going to take our ample, and instead of adding epsilon to it, we're going to add some large multiple of the canonical so that we hit one of these rays, and we're going to use this kind of process and moving around this ample plus RKX to produce this structure. Okay, so that's the picture of the cone theorem. So the upshot is like whenever kx isn't Neff, then you can control the geometry of kx by looking at rational curves on your variety. And in particular, this tells you that if kx is not Neff, there has to be a rational curve. And that's really the starting point of Mori's original proof in the smooth case, was the first thing you want to do is produce a rational curve, assuming only that kx is not Neff. Because of course they have to exist according to this theorem. Okay, so let me just give another definition. I think I gave this before, but these R's these are extremal rays. Or maybe I should say this is a remark, not a definition, meaning that where the definition of extremal that I gave before was that if I have V and W that are in my cone, and I know that V plus W is contained in the ray R, then both V and W are contained in the ray. So that just means that they're on the boundary of the cone. Okay, so then the second piece of this theorem is the existence of extremal contractions. So let F be any extremal face on the kx negative side. That's so in this definition, I could have just one of these rays, but F could also maybe be one of these faces that lives between rays or in higher dimensions. Maybe it's a higher dimensional face spanned by extremal rays, but whatever it is, it's some extremal face, so it's some face on the boundary that's on the kx negative side. I guess for this definition, I don't need to assume kx negative, but we're only going to have the existence of these things I'm about to define in the kx negative case. But it's okay, I'll leave that here for now. then a morphism contraction of f from x to y is called an extremal contraction of f. If it satisfies two properties. The first property, which gives it its name, is that a curve is contracted by this f to a point if and only if the numerical equivalence class of this curve lies in our face. And two, the push forward of O is O. Okay, so that's definition that I guess we can make even if we're not on the kx negative side. But then the contraction theorem essentially tells us that extremal contractions exist when we take a kx negative extremal face. Or extremal ray. So again, this is a special case of a much more general theorem that we'll prove later. Let's say R is a kx negative extremal ray. Then there is a unique extremal contraction of this ray. So it's an existence theorem that if we have a kx negative ray, then we actually can contract it, and if L is a line bundle on X, whose intersection number with all of the curves in this ray is 0, then L is actually pulled back along this extremal contraction. So this is maybe reminiscent of what we just talked about in the case of these canonical contractions as well. There I should have put OI, not OZ. Okay, so that's the contraction theorem. So now the general kind of the starting point of the minimal model program is you prove these two theorems, and now you say, suppose Kx is not an F. Let me look at its cone of curves. It has some rational curve on it that spans an extremal ray. Then by the contraction theorem, I can contract it to something and get a y. And now this y is supposed to be some simpler birational model of x. And then you want to keep going. Now you want to look at the cone of curves of y. If kx is not an f, then you produce another contraction. If kx is an f, you're done. Or maybe your extremal contraction landed you on something that's lower dimensional, and now you induct on dimension and prove whatever you want by proving it on the lower dimensional thing first. So that's what we want. But the issue is that these extremal contractions in this theorem that are guaranteed by this theorem, there's no reason the y's in these extremal contractions are smooth. And in fact, they're not smooth, and the singularities of y can be quite bad depending on what this contraction looks like. So the difficulty then is that we need to generalize the cone and contraction theorems to some y's, and then we need to show that every time we produce an extremal contraction, the singularities of y are not so bad that we can still apply our more general cone and contraction theorems. And this won't always be true. Sometimes the singularities of y will be so bad that there can't ever be a cone or contraction theorem on y, and then we have to produce some kind of partial resolution of y where we can keep going. So that's where we're going from here. So next week, we'll spend one class proving the Cohn theorem in the case of smooth varieties, using this idea of producing rational curves. So we'll use some deformation theory to produce rational curves that give us the Cohn theorem, but that's not powerful enough to actually prove the contraction theorem. So we'll leave that for a little later. And then after that, we'll try to see what type of singularities we need to allow and how to come up with methods that will prove these theorems when we have singularities.